In today's lesson, we want to stop and think quite a bit about what goes on with cyclohexane specifically. And we're going to take cyclohexane and we're going to add in a bunch of different methyl groups to all of the positions and explore the different stereoisomers and then start to compare the heat of combustion data. So all of the compounds that we're going to look at with this table right here are constitutional isomers of each other. So the heat of combustion is a fair comparison regarding the stability of all of these compounds. And if you look at the heat of combustion data right here, you'll notice that they have it in kilojoules per mole and kcals, and we care about kilojoules per mole just for the sake of caring about one of the two. And you'll notice that this cis-1,3-dimethylcyclohexane and the trans-1,4-dimethylcyclohexane end up having the lowest overall heat of combustion. And then we're going to compare that to all of them and try to figure out why it is that what's so special about cis-1,3 and trans-1,4-dimethylcyclohexane that makes them among the most stable of the different dimethylcyclohexanes constitutional isomers. Now, the lesson asks for you to draw these different constitutional isomers, and I'm definitely going to cheat by using ChemDraw. And so we want to look at, here's a cyclohexane, and we want to put methyl groups at the 1 and the 2 position, and let's start there. For this carbon right there, that carbon, we'll call that carbon number 1, I'm going to put a methyl group and I'm going to put it in the axial position. The equatorial position would be right there, and we'll come back to that one later. And then I'm going to put another methyl group at the 2 position right here. Now, it would be equally correct to come over here and put a methyl group, in this position and call it the 2 position, and that would be the equatorial position, and that would be the axial position. But it's kind of easy to work off of either the head or the foot of a chair. Now, this particular 1,2-dimethylcyclohexane, the first thing we want to do is decide if it's trans or cis. The cis conformation does not refer to whether or not both of the methyl groups are axial and equatorial. Cis and trans have nothing to do with whether they're both axial or both equatorial. It has everything to do with whether or not both of the methyl groups are up or down relative to the carbon that they're placed on. So for this carbon right here, this is the axial bond, and this is the equatorial bond. For this carbon, this is the equatorial, and this is the axial. For something to be cis, both of the methyl groups need to be on the same side of the cyclohexane chair, meaning they both need to be up. So this right here, if I put a methyl group there and a methyl group right there, then this would be cis. The other version of cis would be having both of those methyl groups down. So if this methyl group is down and this methyl group is down, then this represents the cis version. We got to make sure to label these with hydrogens, or I'll have to assume that they're methyl groups. So this right here is one version of cis-1,2-dimethylcyclohexane. And the other version would put hydrogens here and methyl groups right there. Both of these represent cis-1,2-dimethylcyclohexane. And the point I'm trying to make is that cis means that they are both up relative to the carbon that they're on, or they're both down. It doesn't really matter if they both happen to be axial or equatorial, or in this case, one of them is axial and one of them is equatorial. That has nothing to do with cis and trans. Cis and trans are all about being up or down. So this is the, whoops, I didn't mean to erase that. This is 1,2. Let's now think about what the 1,3 version of this would look like. So I'm going to go ahead and take the methyl group off and just for now leave it unlabeled. I'm going to call that carbon number 1, and I'm going to walk over to, this is carbon number 2, and this will be carbon number 3. The axial bonds rotate every other carbon. So if this axial is down, then that means that this axial is up. And since it's the third carbon that I care about, this will be the axial that's down at the third carbon. The equatorial needs to be parallel to the line in the chair that is not touching, which would be this line right there. So there's my axial and my equatorial. And I'm ready now to fill in the 1,3-dimethylcyclohexane. If I want it to be cis, then both the 1, okay, and the 3 need to put the methyl group up relative to the carbon that I'm looking at. Okay? Or they could put the methyl group down. Okay? So if this is the up position and the methyl group is at the down position, this also represents the cis 1,3-dimethylcyclohexane. Okay? The R and the S refer to something that we'll have to deal with later on. So I'm going to go ahead and put the label off to the side. So this is cis 1,2-dimethylcyclohexane right here. I'll put the label off to the side. And then I'm going to have the cis 1,3-dimethylcyclohexane. And then while we're at it, let's go ahead and draw in the cis 1,4-dimethylcyclohexane. And hopefully at this point, you're able to do this on your own. So pause the video and take a minute and see if you can come up with a structure of the cis 1,4-dimethylcyclohexane. I'm going to call the foot the 1 position and the head of the chair the 4 position. So go ahead and draw that and see if it matches up with what I come up with. Well, let's see how you did. So here's the chair conformation. At the foot, the axial is always coming down, and then it rotates, so that means the axial is coming up on this position and down on the 3 position and then up on the 4 position. And the equatorial is going to be parallel to the line in the chair that it's not touching, which means that it needs to be parallel to these 2 lines right here. And the same is true on the other side. It needs to be parallel to those 2 lines. So here I'm now ready to show the cis 1,4-dimethylcyclohexane. Cis means that the methyl groups are either both up or both down. On this carbon, up refers to this equatorial position, down refers to the axial position. Over here, up refers to the equatorial position, and down, sorry, I said that wrong. Up refers to the axial position, and down refers to the equatorial position. So now we have the cis 1,4-dimethylcyclohexane. We have all 3 of the cis versions of these ones. And we are halfway done with the cis, because now what we need to think about is what happens when these ring flip. So ring flipping occurs where you take the head of the chair and you fold it down and you grab the foot of the chair and you push it up. And the chair conformations are going to be mirror image reflections of those. So this carbon right here is now this carbon over here. The head of the chair becomes the foot of the chair. And this carbon on this end is going to end up being this carbon right here. And so this is carbon number 1. And carbon number 2, this shoulder is still kind of off to the, kind of behind the foot of the chair. So it's that carbon right there. And I want that to go behind, but ChemDraw puts in front whatever you drew last. So, all right, so now I have my 2 axial positions. So this carbon right here, I have that carbon, and I have axial going up and axial coming down. Let's go ahead and fill in the equatorial. It needs to be parallel to that line and parallel to that line. Right there we go. So now I have axial, equatorial, equatorial, and axial. For this carbon right here, which is now mapped onto this position, when I flip this carbon up, the methyl group goes from being in the equatorial position, it's still up, so it maintains its same orientation as being up here on that carbon, still up on that carbon, but it flips from the equatorial position to the axial position, and the hydrogen goes from axial to equatorial. And over on this carbon, when you rotate these bonds in order to drive that carbon up, it actually rotates this methyl group down, so it's still going to be up relative to that carbon, but now instead of being in the axial position, it's going to be over here in the equatorial position, and this hydrogen, which used to be equatorial, is now going to be axial. So this is the ring-flipped version of this one. And if you go back to the lesson, it asks me to show both conformations for all 6 compounds. So far now I have both conformations of cis 1,2-dimethylcyclohexane. We want to do the same thing now with cis 1,3-dimethylcyclohexane. So I'll put up my mirror image chair right there. And this carbon is now going to map onto that carbon. So the axial will be going straight up and the equatorial will come right there. That's about looks right. Over here, this carbon now maps onto that position. So axial will go up and equatorial will come down. So I took this carbon and I folded it up and it became that carbon right there. And then I took this carbon and I swung it down and it became that carbon right there. The axial and equatorial will flip. So this hydrogen that used to be equatorial is now going to be axial. Notice how it stays up. So relative to these two bonds, the axial and equatorial, the hydrogen is on top. Right? So it's more vertically located in my field of view. It's still more vertically located in my field of view. The methyl group is more, it's lower on a vertical field of view. This methyl group is still lower on a vertical field of view. It's still below the hydrogen. So I kept everything in the right orientation. I just ring flipped it. So the hydrogen went from equatorial to axial. The methyl group went from axial to equatorial. This methyl group is going to ring flip to the equatorial position, and the hydrogen will ring flip to the axial position. I'm going to check to make sure that it's still cis 1,3-dimethyl cyclohexane. So I see the cyclohexane chair conformation. This methyl group can be at the 1 carbon. The other methyl group can be at the 3 carbon. Both methyl groups are down relative to the hydrogen on the carbon they're attached to, which means they're on the same side, which means it's still cis. The last one. If you would like to check your ability to do this, I would go ahead and pause the video, draw your own ring flipped conformation, and see if you match with what I'm going to do. All right, let's go ahead and draw these in. I'm going to care about the same carbons, the 1 and the 4 carbons. So the 1 carbon used to be the foot of my chair, and I folded it up to become the head of my chair. So I want to look at what's axial and equatorial on that. The head of the chair folded down to become the foot of my new chair. So that's my axial, and there's my equatorial. Again, notice how the axials, rotate. So if this one is up, then at the adjacent carbon, the axial will be coming down, and at the adjacent carbon, the axial will be going up, and at this 4th carbon, the axial will be coming down. The hydrogen, when I folded this carbon down to turn it into the new foot, that hydrogen pointed down because of that, and the methyl group ends up going equatorial. When I folded this up, the methyl group ends up going axial, and the hydrogen goes equatorial. So now I have both ring flip conformations for 3 of the 6 compounds that I care about. I chose to start with the cis conformations. Now I'm going to go ahead and repeat the same exercise for all of the trans conformations. And the model should look, I got to come up with both conformations for all of these. And so I'm just going to take these these same structures right here and see if they'll copy and paste. There we go. Only now I just need to start all over again with my labeling. So I'm just going to erase my slate right here. And now instead of cis, I want to focus on the trans. So we'll type in trans. All right, so we got the labels correct. We have our palette ready, and now we just need to start filling in our methyl groups. Trans means that the methyl groups are on the opposite side. So if this methyl group is up, then at the 2 position, the methyl group needs to be down. And I'll put the hydrogens in here. One of the common mistakes that students make when they're looking at these structures is they'll say, wow, those hydrogens are really close to each other. And they're not. The nature is that you can't really see the 3-dimensional aspect of this cyclohexane chair conformation. This carbon is actually further back away from you than this carbon, and this hydrogen is pointing even further back still. So if I would need to show this as a dash, and this one is actually coming a little bit out away from you, so a wedge. So if you were to look at this top down, if you're standing above it and looking down on this chair conformation, that hydrogen and that hydrogen would be not very close to each other. It just so happens that this perspective that we take puts those hydrogens fairly close to each other. All right, we'll go ahead and move on to the next trans arrangement, the trans 1,3. So this one is trans because relative to that carbon, one of the methyl groups is up, and on the other carbon, the other methyl group is down. Trans 1,3 means that one of them has to be up, or in this case, one of them's down, and on the other carbon, I'm going to put the methyl group on the top position, and then the hydrogens should follow suit. And for trans 1,4, I'll put this methyl group up, and then I'll put this methyl group down right here. We'll go ahead and ring flip this. This carbon, I'm going to kind of ratchet it up, and it becomes that carbon right there. And when I do that, when I pull this, rotate this carbon and kind of rotate my bonds and spin that carbon up, that ends up putting the hydrogen on the top axial position and the methyl group out here in the equatorial position. And if you still can't see that, then you just have to memorize that when you ring flip something, everything that used to be equatorial is now going to become axial. And everything that used to be axial is now going to be equatorial. Methyl and hydrogen. And once again, it might look like this hydrogen and this methyl group are very close to each other, and that's just because you're thinking about it in 2 dimensions. It has 3-dimensional depth to it, and that methyl group is pointed quite a ways away from that hydrogen right there. When I ratchet that carbon up, the hydrogen goes from equatorial over here to axial right there. The methyl group goes from axial to equatorial. And when I pull that carbon down, it rotates this bond and slides that methyl group up. And there is my hydrogen. It's still trans because on this carbon right here, up is the methyl group and down is the hydrogen. And on this carbon, up is the hydrogen and down is the methyl. So one methyl is up, one methyl is down. Remember, cis and trans have nothing to do with axial and equatorial. Cis and trans are all about up versus down. When I rotate this one, the methyl group goes from equatorial to axial. The hydrogen goes from axial to equatorial. Pull this one down, the hydrogen ends up equatorial, and the methyl group ends up axial. All right, so now I've drawn both conformations of all 6 of my isomers of each other. Okay, the next part of this lesson asks me to identify which conformation is more stable for each compound. So it's asking me to compare conformational pairs. So this is a conformational pair with this compound. All of my conformational pairs are horizontal. Just to make sure you're aware, these horizontally are my conformational isomers, sometimes just called rotamers or rotational isomers or conformers. Horizontally, these would be constitutional isomers of each other. To get from cis 1,2-dimethylcyclohexane to cis 1,3-dimethylcyclohexane, I would have to pop this methyl group away from this carbon, move it to an entirely different carbon, and reattach it. And that's the definition of a constitutional isomer. So these 3 are all constitutional isomers of each other. The stereoisomers are where we compare the top line of the cis with the top line of the trans. So cis 1,2-dimethylcyclohexane and trans 1,2-dimethylcyclohexane, those are stereoisomers of each other. Cis 1,2-dimethylcyclohexane is a constitutional isomer with trans 1,3-dimethylcyclohexane, because to get from this compound to this compound, I would have to snap that methyl group off and reattach it to a separate carbon. Stereoisomers occur when you snap the methyl group off and reattach it to the same carbon in a different position. I just kind of moved it down to the bottom. So that conformational isomers are horizontal. Most of everything else is a constitutional isomer, but there are 3 pairs of stereoisomers. The 1,2-dimethylcyclohexane cis and trans are pairs of stereoisomers. 1,3 cis and trans are pairs of stereoisomers, and 1,4 cis and trans are pairs of stereoisomers. So the question didn't ask that, but that's how we use those words. That's what they mean to us. All right, let's reel back from that tangent a little bit and get back to the question at hand, and that's which of these 2 conformational isomers is more stable. And what we're looking for is the isomer that puts the largest amount of carbon mass in the equatorial position. So for example, cis-1,2-dimethylcyclohexane, in this conformation, one of the methyl groups is equatorial and one of the methyl groups is axial. So this one over here, we can call it axial equatorial. For this one over here, this methyl group is equatorial and that methyl group is axial. So it's still axial equatorial. And what this means is that there is no energetic difference between these two conformations. They are both equivalent, and the molecule will spend 50% of the time in one conformation and 50% of the time in the other conformation. Well, it's not quite 50 because there is some of the time that's spent flipping back and forth between the two conformations, but it's still going to round to about 50% of the time in one conformation and 50% of the time in the other conformation. So when you're asked which one is more stable, then these two conformations, two conformers, are equally stable, okay? Because both of them put one in the axial and one in the equatorial. All right, cis-1,3-dimethylcyclohexane. Notice how this one has 2 in the axial, and over here when we ring flip it, now 2 are in the equatorial. So now we're comparing a conformation where it's axial-axial with a conformation where it's equatorial-equatorial. And over here, the equatorial-equatorial is the much more stable conformation. So I'm just going to put a box around this, indicating that this is the more stable of the two. And what that means is that the molecule spends approximately 0% of the time over here in this conformation. So when we want to talk about how cis-1,3-dimethylcyclohexane acts in a solution doing chemistry, we're going to think about it like this, and we're not going to think about it like this. Yes, some of the time it will spend axial-axial, but that some of the time is such a small percentage that this over here really explains the behavior of the compound essentially 100% of the time. It just spends most of its time like this. And the cis-1,4-dimethylcyclohexane is going to be axial, equatorial, and equatorial-axial. So it's going to have the same characteristics as cis-1,2-dimethylcyclohexane. So we'll see if we can just kind of copy those labels down. Now for the trans-1,2-dimethylcyclohexane, in this conformation, it's axial-axial. And in the other conformation, it's equatorial-equatorial. So I'm just going to steal all of these labels, and hopefully they fit. Oh, they do. Very nice. So again, trans-1,2-dimethylcyclohexane is not a mixture, we don't think about it as if it were some of the time it's axial-axial and some of the time it's equatorial-equatorial. We actually just think about it as essentially all the time it's got both substituents in the equatorial position. And if it does happen to be over here in this orientation or this conformation, it just kind of flickers and then immediately right back to equatorial-equatorial. So this is going to describe the molecule in terms of how we want to think about it. This compound has one in the equatorial and one in the axial. Therefore, when we ring flip it, it goes axial-equatorial. So the two conformations are going to be equally stable, and it will spend an equal amount of time kind of flipping back and forth between the two. And then trans-1,4-dimethylcyclohexane, here is where both of them are equatorial, and over here is where both of them are axial. This therefore becomes the more stable conformation where they're both in the equatorial position, and the molecule essentially acts like this all of the time. All right, now I'm ready to incorporate all of those structures into my lesson answer key. So I drew both conformations for all 6 of the compounds, so that's 12 total structures. And then for each conformational pair, I identified which one was more stable. Or in cases where they're both the same, then I just made that note. So here I have kind of now a nice listing of which conformation is really more helpful. The third part of this question asks me to explain differences and similarities between heat of combustion values for each stereoisomeric pair. And let's get rid of some of the clutter now. Specifically, when we have this conformation for cis-1,3-dimethylcyclohexane, where both of them are axial, the point that I tried to make was this really doesn't represent any meaningful way of thinking about the compound. It's going to act like this most of the time. And so we're going to go ahead and kind of strip down the axial. We're going to get rid of them entirely. We just don't really need them because that doesn't explain how the molecule acts. So, and then for the other three, because one of them is always going to be axial and one of them is always going to be equatorial, it's kind of redundant to show both of the conformations for this last question right here. So I'm also just going to kind of randomly get rid of whichever one here I don't want. And I'll get rid of that one. So now what I'm doing is I'm kind of looking at the 6 compounds right here. Okay? In the case where they're axial and equatorial, then I'm just going to look at one of the two. In the case where it's either axial or equatorial, I'm really only going to consider the equatorial ones. And so now let's kind of sort them based on pairs. I'm going to put the cis 1,2-dimethyl cyclohexane, and I want to compare it to the trans 1,2-dimethyl cyclohexane. These are a stereoisomeric pair. And I'm going to do the same for the cis 1,3-dimethyl cyclohexane, and I'm going to compare it with the trans 1,3-dimethyl cyclohexane. And finally, the cis 1,4-dimethyl cyclohexane, compare it with the trans 1,4-dimethyl cyclohexane. And so now I'm just looking at stereoisomeric pairs. This is different than the last comparison that I made because in that case I was just trying to pick which conformation was most meaningful. Now I'm actually looking at stereoisomeric differences. In order to determine which of the two stereoisomers is more stable, I'm still going to use the same axial versus equatorial criteria. So for trans 1,2-dimethyl cyclohexane, this methyl group is equatorial and that methyl group is equatorial. Equatorial is going to be a more stable conformation because putting methyl groups in the equatorial position reduces the steric hindrance. When I have the cis 1,2-dimethyl cyclohexane, one of the methyl groups will be axial and one of the methyl groups will be equatorial. And so this right here is the more stable of the stereoisomer. So it's the more stable stereoisomer. And the reason I want to use my words carefully here, stereoisomer and not conformational isomer, conformational isomers can just kind of flip back and forth. Stereoisomers can't. If you had a bottle full of trans 1,2-dimethyl cyclohexane and shook it, it would not rearrange itself to cis 1,2-dimethyl cyclohexane, and vice versa. These are two separate molecules, and they have different characteristics. Whereas the different conformations just kind of interconvert back and forth between each other. So this is the more stable stereoisomer because it's got this equatorial arrangement. Now, a student might ask, well, doesn't it also have an axial arrangement? And the answer is, yeah, if something is equatorial, that means when you ring flip it, it's going to be axial. But the axial is such a kind of a flickering moment of time that it doesn't actually explain the stability of the compound. We're going to focus on how the compound behaves the majority of the time. For the trans 1,3-dimethyl cyclohexane, this methyl group is axial and that methyl group is equatorial. So it's axial, and if I ring flip it, it's still going to have one of them in the axial and one of them in the equatorial. Cis 1,3-dimethyl cyclohexane puts both methyl groups in the equatorial, so that means that of the two stereoisomers, the cis 1,3-dimethyl cyclohexane is your more stable stereoisomers, and I'm doing horizontal comparisons right here. In the last comparison, it's trans 1,4-dimethyl cyclohexane, and this is cis 1,4-dimethyl cyclohexane. This is axial and equatorial, whereas the trans is equatorial and equatorial. So in this case, the trans happens to be the more stable stereoisomer. And usually at this point, when I write all this on the chalkboard, a student raises their hand and says, so the trans is always more stable than the cis, at which point I give up. No, it's not. Notice how the middle one right here, the cis is more stable than the trans. Stability with cyclohexanes is not due to being inherently cis or trans. It has to do with whichever stereoisomer can put substituents in the equatorial position. It's always about equatorial and axial. Okay? So now we've answered part of the question. So comparing the stereoisomers right here, We've identified that for 1,2-dimethyl cyclohexane, the trans happens to be more stable because they're both equatorial. In 1,3-dimethyl cyclohexane, it's the cis, and in 1,4-dimethyl cyclohexane, it's the trans. Does it just alternate back and forth? Well, yeah, for cyclohexane, sure, because there's only 3 possible pairs. But if you were to try to apply that same logic to cyclopentane or cyclodecane, I don't know. You'd have to go through and do the structural analysis. And fortunately for you, the only one we really care about is cyclohexane. So if none of this made sense to you, for one, I'm sorry, but you could just memorize the answers to these pairs right here. So in a pinch, you just memorize a bunch of stuff. Before we move on past letter C, there's actually one more thing that shows up. And notice how cis 1,3-dimethyl cyclohexane, its heat of combustion is 5,212. For trans 1,4-dimethyl cyclohexane, its heat of combustion is also 5,212. So what I'm saying there is that this compound right here, cis 1,3-dimethyl cyclohexane, has the same heat of combustion and is therefore equally stable as trans 1,4-dimethyl cyclohexane. And that should make sense. Both of them can put their methyl groups in the equatorial position. And therefore, we would expect cis 1,4-dimethyl cyclohexane and trans 1,3-dimethyl cyclohexane to both have the same energy as each other, because one of them will always have an axial methyl group and an equatorial methyl group, and so will the other one. And we also expect both of those compounds to be slightly higher than both of these compounds. And that's what we see with the data. That because cis 1,3-dimethyl cyclohexane puts both of its methyl groups in the equatorial position, its heat of combustion is lower. And trans 1,3-dimethyl cyclohexane puts one axial, one equatorial, and therefore its heat of combustion is higher. The odd one is when we look at cis 1,2 and trans 1,2-dimethyl cyclohexane. Notice that the di-equatorial version, the trans 1,2-dimethyl cyclohexane, has a heat of combustion value that is still lower than the axial equatorial versions of 1,3 and 1,4-dimethyl cyclohexane, but it's actually a little bit higher, and a fair amount higher, than the di-equatorial versions of 1,3 and 1,4, and this is because of sterics. These two methyl groups right here on 1,3-dimethyl cyclohexane are far enough away from each other that they're not bumping into each other, even when one of them is axial and one of them is equatorial. The same thing is true over here with these methyl groups at the 1 and the 4 position. But the methyl groups at the 1 and the 2 position are now starting to bump into each other. So what you're seeing in the data table is a small penalty for the 1,2-dimethyl cyclohexanes due to the steric collisions between their methyl groups that is not found in the 1,3 and 1,4-dimethyl cyclohexanes, where we can separate those methyl groups further apart. So I'm going to take this. Well, I'll just add something in here. So for each stereoisomeric pair, I've identified the more stable stereoisomer and justified my choice of calling it the more stable stereoisomer by pointing out how both of the methyl groups are equatorial. But this one has an added issue, is there is additional steric collisions or strain or interactions between the methyl groups. And this explains why we see slightly higher value for both of these stereoisomers compared to the other 4 stereoisomers. And that slight increase is not due to the axial equatorial issues, it's simply an issue of steric strain. So that's why I'm explaining differences and similarities between the heat of combustion values for each stereoisomeric pairs. And so I'll drop that figure in there, and that should provide an answer to part C. Okay, moving on. So next we want to name the compound, determine which of the 2 shown conformations is more stable, and then explain the choice of the stable conformation. So for naming this one, this is some type of cyclohexane. On one of the positions I have a methyl group, and on the other position I have an isopropyl group. If I call this carbon number 1, then my locant pattern is 1 and then 2. If instead I call this carbon number 1, then the locant pattern is 1, 2. So it's going to be 1, 2 going either direction. When the locant pattern is the same going either direction, you choose the number that gives you alphabetically the letter with the higher priority, and we alphabetize this one by the letter I. ISO is not a numeric designation, so I'm going to give the I the number 1, and I'm going to give the M the number 2. I also need to put these in alphabetic order, so the isopropyl is actually going to come, see if I can cut that out. Nope. Well, so the name of this would be 1-isopropyl 2-methyl cyclohexane. So that's the name. And it's going to be the same name regardless of which of these two compounds I look at. But if you remember from the previous question, now we need to think about the world in terms of cis and trans. And this is unique to ring-containing compounds, and we'll see later with alkenes. We have to ask, because there's two different ways of looking at 1-isopropyl 2-methyl cyclohexane, and that's cis 1-isopropyl 2-methyl cyclohexane, or trans. So in order to determine if it's cis or trans, I look at the carbon that the methyl group is coming off, and I ask if the methyl group is up or down relative to that carbon. And the answer is it's down. Over on this carbon, the isopropyl group is also down. And if both groups are down on their respective carbons, then this is going to be a cis compound. So this right here is cis 1-isopropyl 2-methyl cyclohexane. And this compound over here should also be the same. The isopropyl group is down and the methyl group is down. This is still the same. And just ring flipping it shouldn't change from cis to trans. So I'm just double checking that I didn't mess up my structure or my name right here. So that's the correct name for this compound. We're going to determine which conformation is more stable. Well, both of these conformations have one substituent in the axial position and one substituent in the equatorial position. So the comparison isn't just looking for the conformation that puts both of them equatorial. This methyl group is equatorial, this isopropyl group is axial. Methyl group is axial, isopropyl group is equatorial. But you might guess what the right answer is simply as a function of steric mass. This isopropyl group is huge, and it will exert more steric strain in the axial position than the methyl group will in the axial position. Not all substituents are created equally. And the short answer, and all the examples I'll show you, is you choose the conformation that puts the highest number of carbons in the equatorial position, equatorial. So here, the isopropyl group with its 3 carbons is equatorial, and my methyl group with its 1 carbon is axial. So the right-hand side shows me 3 carbons equatorial, 1 carbon axial. On the left-hand side, I have 3 carbons axial and 1 carbon equatorial. And so the right compound is more stable because 3 equatorial, 1 axial carbon is more stable than 3 axial, 1 equatorial carbon. Now, I'm sure there are examples where putting the largest number of carbons in the equatorial position doesn't actually produce the more stable conformation, but I will carefully avoid showing you any of those examples in this course. We're just going to look at it in terms of simple rules, because if you want to get to more complicated rules, then you have to run calculations, and those calculations are usually done on a computer, and that's just not the focus of the course. Explain your choice of the more stable conformation, and so that's what's in parentheses up above. And so I'll just put a note here. More carbons equatorial is good. And we'll just attribute that to Grog, because that's exactly how a pre-literate human might say that. Okay? All right. The last example is just kind of a intellectual curiosity. What happens if you have more than 6 carbons? And so first we want to name this compound. And let's see. I see in a ring structure there's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbons. So that means that this is going to be a cyclooctane. And I don't see any methyl groups or anything else coming off of this cyclooctane. So that's what it is. It's cyclooctane. And what are the different types of strain associated with the specific values? Okay, so what you'll see right here, so I have identified the values that are problematic. And this is an attempt to show kind of a chair conformation for cyclooctane. So you can see sort of the head of the chair right here, and then there's the seat of the chair, and then the foot of the chair has some kind of tumor coming off the side. So this is just an ugly chair, and that's because cyclohexane is the only compound that has a true chair conformation, and everything else tries to mimic it. And what I did to make this compound is I built cyclooctane in ChemDraw 3D. I ran an energy minimization program, and this is kind of the best case scenario of what the calculations for cyclooctane showed me. And then I went in and explored the compound using features of ChemDraw 3D that I've since forgotten about. But it allowed me to find the exact bond angle. And this right here is a bond angle of 117 degrees. And so for part B of this question, the 117 degrees represents bond angle strain. That's why I've kind of highlighted that one. The ideal bond angle in an sp3 hybridized carbon is 109.5 degrees. And so we could actually quantify, represents, let's see, 117 minus 109.5 is 7.5 degrees of bond angle strain. And that's something. And that what this means is that the compound actually absorbs some bond angle strain in order to accommodate the other types of strain that exist within the compound. And in 3 dimensions, also I noticed that this hydrogen right there and that hydrogen were getting kind of close to each other. The ideal distance, kind of minimum distance between 2 hydrogens is right around 2.4 angstroms, or 240 picometers. And so that number right there that says 210 picometers represents a steric collision of hydrogen electron clouds. And the 220 represents another steric collision of hydrogen electron clouds. So that's sterics. What we're looking at there is just a steric problem. And we have a bond angle problem. So if you remember, the cyclohexane was that sweet spot for the most stability. And when you start getting larger than cyclohexane, you start introducing things like angle strain and steric problems. Even in cases where all you have are hydrogens, you still have steric issues. And that just kind of illustrates that idea that cyclohexane is the best and everybody else has some kind of problem. I think this is the first lesson I've shown you where I didn't have definitions for you to fill in. I just summarized kind of the key concepts we're looking at today. We talked about the stability of polysubstituted cyclohexanes. We spent most of our time looking at the different versions of dimethyl cyclohexane, whether it was cis, trans, 1, 2, 1, 3, whatever. We looked at those 6 different compounds. And then we also looked at the larger cycloalkanes. For example, this example here, where number 2, where we put a lot more on the outside of a cyclohexane, or we just went up to cyclooctane and saw how ugly things get very quickly. So we like to kind of stay right with cyclohexane and then think real hard about what's going on with cyclohexane. For the chalkboard problems, what I've done, this question kind of gives you the answer and then asks you to justify it. So here, this can ring flip in such a way that either the hydroxy group is in the axial position or the methyl group is in the equatorial position. And if you ring flip it, then the hydroxy group would be in the equatorial position and the methyl group would be in the axial position. And it says the methyl group has a greater preference for the equatorial position than the hydroxyl group, and you need to think about why. And then for the second part of this question, and there's hopefully 5 different students will submit answers for this. You need to draw the ring flipped version of the ring that I've given you and then decide which of those 2 conformations, the one that I've given you or the one that you fill in, ends up being more stable, and then why. And you're going to spend some time counting carbons just like we did here in question number 2, where we tried to put having more carbons in the equatorial position, is generally more stable. That's what you're shooting for in the chalkboard problems.